We finished through the reading we had for today. I don't want to start the heat, energy, endothermic, exothermic. Those of you that have read ahead, I don't really want to start that today, per se. We did have homework, review questions, and practice problems that should be back there. So I'd like to go ahead and do those. Go ahead and turn this around, maybe get a little bit better audio. Go through the review questions and a couple practice problems as our primary, and then maybe another fun activity after that. Because I know, if you notice, I didn't put it in I now, because if I put down every homework in I now and every quiz in I now, and then we don't have it, parents feel like I'm ripping you off from the educational opportunity. So I didn't confine myself in that way. But day 4 is what we're on the schedule for this module, and so it's homework and then another fun activity. Review questions 3 through 10, practice problems 1 and 2. Before we get going, any major tensions, issues, things you don't understand that you want to address now, or maybe they'll come up during the review. Either way, you will work it. So, does anybody have a question right now they'd like to cover? Any material you'd like to cover right now? It's amazing how loud that can actually be on the recording. Those weird sounds in the background. What is that? No? Then we go to review question number 3. What's wrong with this statement? It does not matter what the solvent is in determining solubility. It does matter, right? It's a pretty hard one to figure out. There's a logical inference there that is wrong. What is wrong with it? It does matter. It matters what the solvent is. It also is unique to the solute as well, right? So it's referring to a single solute here, saying it doesn't matter about the solvent, but it does. Because ultimately, solubility, we're talking about dissolving things. The nature of dissolving is molecules putting themselves between other molecules, or molecules pulling other molecules together. And so the nature of both the solvent and the solute is highly significant in terms of solubility. So it matters what you're dissolving, and it matters what you're dissolving into. And it matters what the temperature and the pressure are as well. What is a saturated solution? A saturated solution. We made one yesterday.
Something that's been dissolved all the way through it.
A little bit louder though. It's dissolved all the way? Is it?
Dissolved to like the maximum.
Right, it's dissolved. The maximum amount of solute is in solution. Is one way to say it. So the stuff we're dissolving into, yesterday we used the sodium chloride in water, the salt, and we mix it up to hold as much as it can hold. And that's when we put way too much salt in, remember? And we had to filter it out. If you think about it as a reaction, which it's not a reaction, but if you make an analogy to a reaction, we had excess sodium chloride with the water. Now the water and the sodium chloride were not reacting, but there was way more salt in there than that water could hold at that pressure and at that temperature. We know that because no matter how much we stirred it, there was still salt on the bottom of the mixture. When we filtered that through and we had cloudy water, we knew that we had water, and we figured out later on that what the cloudiness was were the sodium and the chlorine ions in the suspension in that solution, right? They were there in that solution. So it could not hold any more than it was holding at that time. Later, after we chilled it, what did we find at the bottom of the beaker? You know, brought it out of the freezer and passed it around. What did you see at the bottom? Sodium chloride molecules had precipitated, vocabulary word for this module, had precipitated out of solution. What had happened? The solubility had changed because of the temperature change. And what's the general principle about solubility and temperature for solids?
The temperature decreases, solubility decreases.
Correct. They're directly related. As one goes down, as temperature goes down, solubility goes down, which means we went from holding as much as it could hold to, technically speaking, it had more than it could hold. And when it had more than it could hold, it dropped it. It precipitated it out. So it precipitated out sodium and chlorine ions, which found each other and reformed sodium chloride molecules. Those molecules found each other and formed grains when they came together. Okay? So the saturated solution is a solution that has the maximum amount of solute that can be dissolved at that given temperature and pressure. Number 5, within the topic of solutions, what is precipitation? I just mentioned it, but say it again in your own words. What is precipitation? And what have I encouraged you in here to think of precipitation as if you forget? What does it mean for something to precipitate? Well, look at the poster back there above Kyle's head. Those are different kinds of cloud formations, right? And there's certain ones on there you would expect certain kinds of activity from. The big cumulonimbus right there with the anvil head on it, on the top. If you saw that in the sky, what would you think is coming? You see it right there? The large in the middle, towering at the very top, it pushes over. It's called the anvil head on the top, where it pushes over. I used to teach meteorology too. So, what would we expect some of those clouds? Certain kinds of clouds have certain kinds of weather conditions that follow them, right? Okay. And one of the conditions that tend to follow clouds. What is a cloud?
What is a cloud?
What is a cloud? It's not sheep wool. It's not cotton balls. It's it's impending precipitation. It's water vapor, right? It's water in a gaseous state. Water stays in the air. You can, to a degree, think of the water vapor as a gaseous solute in the air around us, which is the solvent, right? But it's not truly that way. It's, again, another analogy. At a certain point, there's as much water in the air as the air can hold. And as conditions change, matter of fact, in the same way that when we took the sodium chloride and put it in the freezer and salt precipitated out, in the same way, a cloud represents water vapor, that as the conditions around it change, at one point, the air was able to hold all that moisture, but at another point, the conditions have changed, and suddenly, or maybe not so suddenly, depending upon certain conditions, but the conditions have changed, and there is now more water in the air than the air can hold. So the air drops it. It precipitates it. We know it as precipitation. Another word for precipitation in meteorology is you can go back and watch the video. I went over this a couple different times. What is precipitation?
When it changes from solid to liquid. Or
It's from a gas to a liquid, and its precipitation is called rain. Rain is precipitation. It's also snow. Snow is rain under different conditions, right? So the rain is liquid water. It could come down as frozen water. Frozen water comes down as hail or snow or sleet. If it comes down as liquid, but then it freezes, like freezing rain, what does that tell you about the temperatures? Again, we're wandering into meteorology now. If it comes down as rain and then freezes, is the ambient temperature high, altitude warmer than low? You know, there's a lot of times it's technically raining out of the clouds, but we never feel it down here. There's water falling from the clouds, but before it comes all the way down, it re-evaporates. Because the conditions up high, it can't hold all that water, but the conditions before they hit you can take the water in. And so sometimes watching the weather, you'll hear about precipitation, which is re-evaporating before it hits the ground. So it's raining at altitude. If I were to take my helicopter and fly through there, I would be hit with rain. But on the ground, they don't know it's raining because it evaporates before it hits the ground. Okay, so just because it drops it at altitude doesn't mean it makes it all the way to the ground. But that act of dropping something, in this case, water being dropped by the air, it's precipitating out the water. the water is going from a vapor to a liquid. And it may then, once it's a liquid, convert to a solid, or it may stay as a solid, or on the way down it may revert back to being a gas and just never hit the ground. It just re-evaporate into the air. That's where you get different layers. Air moving back and forth. Conditions at one layer aren't the same as conditions at another layer. This has too much water. This one might be able to hold more. And so as it passes through that layer, it re-evaporates into the air. So precipitation is the solute being released or coming out of solution. The solute is coming out of the solvent. Dissolving, is it going in? Precipitation, is it coming out? Okay, so those are two ways the solvents and the solutes interact. Solvent going into solution is dissolving. Solute coming out of solution is precipitating. Number 6, what kind of solute, liquid, solid, or gas, dissolves the best under high temperature conditions? So we've got the 3 phases of solute, right? Solid, liquid, gas. High temperature, which one has the better solubility? More will dissolve of what phase with a high temperature? Really appreciate your participation. Okay, let's give some other people a chance too. But you're right. It's a solid, just like with the sodium chloride. As we increase the temperature, so maybe let's take a step back again. What is actually happening when a solid is dissolving? A solid is dissolving. What is the solvent doing to the solute? I know you know this, but is there something else?
No, I was going to.
Let's give some other folks a chance to participate. And that's a compliment to you, not a diss, okay? What is happening when a solid is dissolving? What is this? When a solute is dissolving, what is the solvent doing for a solid that is dissolving? Just plain language, don't get real technical. What is actually happening? Let me break it down a little bit. Have we covered this already?
Yes.
Have we covered it in detail?
Yes.
Have we covered it more than once?
Yes.
Okay. So those are all yes. Thank you for participating on that one. Those are all yeses. So this is stuff we've covered many times, several times at least. And we've covered it in detail. And we've covered it slowly. Okay. So let's now try to pull that from our memory banks. What is happening when a solid solute is dissolved in a solvent? What is the solvent doing to the solute? Yes, sir.
Separating it.
Separating out the individual, if it's covalent, right? A covalent solute, what is it breaking down into? For a covalent solute, the covalent solute dissolves down to what level? Covalents dissolve down to the individual molecules. Ionics dissolve down to the ions. Okay, so think of it this way. The ionic compounds go one step further, right? The covalents stay together. We use the pH3 molecule as our example there. If you go down to the molecular level, when it's fully dissolved, we will find individual pH3 molecules. Sodium chloride, ionic, when it dissolves, when we go down to the molecular level, we would find individual sodium ions and chloride ions. Because ionics dissolve to the ion level, covalents dissolve to the molecular level, a molecule. So what kind of solute dissolves best under high pressure, high temperature? That's number 6. The solvent getting between the molecules of the solute, or the ions in the solute, is based upon energy, right? The energy to get in there, the energy to make this stirring mixing motion, to separate and to conquer by dividing. That increases with temperature. So in the same way that we could have taken, think of the refrigerator experiment in reverse. If we had taken the water out of the refrigerator or freezer when it was cold and had warmed it up, we could have eventually warmed it to the point where all of that salt that had dissolved to the bottom would go back into solution. Because as we warmed the water, we increased the solubility of the salt in water. So we had it as cloudy salt water. We put it in the freezer, precipitated out the sodium chloride. So at that point we brought it back out. If we'd mixed it up, it's not going to take the salt back. The solubility is low because the temperature is low. But before, when the temperature was high, the solubility was high. Had we heated that beaker back up, over time, as it heated up, we would see the salt from the bottom dissolve, or we would see, by virtue of it disappearing, that the salt went back into solution as the temperature went up. So for solids, a higher temperature means a higher solubility for solids. For liquids, what's the relationship? For solids, higher temperature means higher solubility. Okay? Higher solubility, remember, means more will dissolve. There's a higher solubility. So for a solid solute, for salt in water, that's your example, think of. As the temperature increases, more salt can be dissolved. If, rather than using salt, which is a solid solute, we put a liquid solute in there, what would be the effect of increasing the temperature? Nothing. Liquids are already free-flowing and moving. Liquids just have to be next to each other, and they start to dissolve because the molecules are already in motion. And while they're already in motion, they will occasionally change places, and they'll bring solvents between solute, and they will automatically mix. The temperature doesn't have any major effect. But when we get to gaseous solutes, what's the effect of temperature? Increasing temperature does what? How does it affect the solubility? Decreasing solubility, and yesterday we saw that by putting the soda into hot water. What happened to the rate of bubbling? It went up. When we put the soda in hot water, the amount of bubbling went up. What is the bubbling? It is losing, it's precipitating, if you will, the carbon dioxide. The carbon dioxide is coming out of solution. Why? Because the solubility just went down. So for a gaseous solute, as the temperature goes up, the solubility goes down. For a solid solute, as the temperature goes up, the solubility goes up. For a liquid, we're going to say for this course, there's no real change. Okay? Because the next question, number 7, isn't asking about dissolving under different temperatures. It's talking about which one dissolves best under high pressure. High pressure. Now, which of the phases are affected by pressure? Are solids affected by pressure changes? Do you get more or less salt dissolved because the pressure is higher or lower? No. No change. What about liquids? No change. So the only thing we're talking about that can have an effect is gases. What's the effect of solubility based upon pressure for a gaseous solute? As you increase the pressure, solubility moves in what direction? Increases. As pressure increases, solubility increases. And that is based, again, on the nature of a gaseous solute. How does a gas dissolve? It's the opposite of a solid. A gas dissolves because you're able to get the molecules of the gas closer together. For a solid, it dissolves because you're able to get the molecules of the solid farther apart. Okay? Pressure is squeezing things together. So for a gaseous solute, you help it to stay in and get into solution by pressing it close together. And the analogy there was carbon dioxide in soda in the can. The bubbles stay in. Like if you had a clear can. I hope you have to believe this. It's kind of like, do you know your refrigerator light is off when the door's closed? You assume it is, right? Well, in the can, because it's under pressure, the carbon dioxide, if you were to see through a clear can of soda or clear bottle, like we've got bottles like the one I had yesterday, you're looking inside there, you don't see bubbles. You don't see the top being full of a gas and the bottom being full of a liquid. It looks like it's a liquid from the bottom all the way to the top. And yet, when we open it up, bubbles come out. Do the bubbles just spontaneously come out of nothing? Or were they actually there before, but just weren't visible? You'd argue that they were actually there before. We just couldn't see them. Why? Because they were broken down at the individual molecular level. Carbon dioxide is a covalent molecule, right? As a covalent molecule, it's only going to break down when it dissolves down to the carbon dioxide molecule, not into carbons and oxygens, but down to carbon dioxide. And so while it's in the bottle and the pressure is pushing in on it, it's staying in the solution, and so it looks like just a liquid. However, when we take the top off, suddenly we decrease the pressure. The pressure of the atmosphere pushing down on that bottle is less than the pressure inside that was pushing out. So we take the cap off, suddenly that solution is under less pressure. When that gaseous solute is under less pressure, it is less soluble. What does that mean? The liquid has to drop it. And when it drops it to get rid of it, rather than it falling to the bottom, they have a less density than the solution, and they rise to the top. So by decreasing the pressure, we force the solute, the gaseous solute, out of solution. And so thinking this question again, what kind of solute dissolves best under high pressure? It's the gaseous. Why? That's the only one that really has an effect. The other ones aren't affected by pressure. The gases, high pressure, low temperature, so that's what they want. The colder the liquid and the more pressure on the liquid, the better the gas will stay in solution. If you take the pressure off or you heat it up, the gas goes away. And that's why an open bottle of soda goes flat. And that's why once it's open, a warm soda is flatter than a cold soda. As soon as you open up on a hot day and it's warm, more bubbles are going to come out. You're going to lose it in the opening. You're going to have that immediate depreciation. Like a car, you buy it, as soon as you drive it off the lot, it's not worth nearly what you paid for it. Warm soda, you open it up, you lose all the carbon, or a lot more of the carbon dioxide right away. You open up a cold can, you open up a warm can, give them a few seconds to stabilize, the warm soda will be flatter than the cold soda, because the cold soda is able to hold the carbon dioxide in solution better than the warm. So a warm, open container is the opposite of a cold, closed container, right? Opening it reduces the amount of carbon dioxide in the solution, and warming it reduces the amount of carbon dioxide in the solution. That's why at that party, that 2-liter bottle that's left on the table, with only that much left in it, that's been sitting there in the sun, you don't want that. Not because it's warm. You can take it and put it on ice, it's still going to be flat soda. Okay? Because all of the carbon dioxide has, not all, but virtually all the carbon dioxide has been precipitated out. It has been extracted from the solution. Now all you have left is sugar water. What kind of a solute, solid, liquid, or gas, has a solubility that is least affected by the conditions under which the solution is made? Liquid. It's the only one remaining, right? We've just talked about in detail about gases, and we know about the solids, how temperature affects those. For both those cases, pressures and temperatures, we've said basically that liquids are not really affected compared to the other two. So they have the minimal effect, minimal change. So it would be liquids are least affected by condition changes. Number 9, if a solid solute is not dissolving well in water, what can you do to increase its solubility?
Which one is this?
We are on number 9. How do we increase the solubility of a solid?
Increase heat.
Go ahead. Yeah, just heat it up. Okay, you guys fancy yourself as being in the South. You know, that's a big debate. You know, when we met this new family this past weekend, like Louisville, they're confused about Louisville and Kentucky, and yeah, it is confusing. They're not really a northern state, not really a southern state. You're kind of like that middle ground. For certain things, you want to be southern, so you play southern. And certain things, you want to be northern, you play northern. Okay, so you kind of get a very eclectic kind of culture here. So we get to this issue of sweet tea. I grew up drinking iced tea, but I hardly ever had sweet tea. We don't put Miss Baker. I mean, she grew up in a house where they had to use Clorox to clean out the plastic pitchers because the tea was so dark. It was dark like coffee dark, no sweetener. It was straight dark. Her father would put the tea bags, leave them in the pitcher, and the tea bags were in there until the liquid was gone. So it was constantly steeping in the fridge. Constantly steeping. Really, really. So I come along and I obviously, Mr. Kevin brought me that bag full of sugar and cream. Because, yes, I was in the Marine Corps, retired from the Marine Corps, but I was an officer, so I was kind of pampered. And if there was sugar around, I would get the sugar, so I used it. Why not make it a dessert drink if you can? In our house, the joke is, Mrs. Baker will say, ooh, that's too sweet, or that's too rich, and I'll go, no such thing. It doesn't happen. I've got the worst teeth, too, by the way. But anyhow, so this idea of sweetening a drink, have you had the experience of trying to dissolve sugar in cold iced tea? You have a cold iced tea and you decide you want to put somebody gives you iced tea and you forget to ask for sweet tea. They bring it to you cold and unsweetened. And now what do you have to do? You've got to try to get that sugar, pour it in the glass and try to stir it up and try to get that sugar to dissolve into that cold liquid. Okay. What's a smarter thing to do? Take that tea while it's still hot and put sugar in it, right? Because you put that that sugar into the hot tea, it doesn't even hit the bottom of the pitcher. It dissolves on the way down. Why? The warm solute, in the warm solvent, because it's a solid, dissolves quicker. It has a higher solubility. You want to get really radical about it. Try to dissolve as much sugar as you can in it while it's warm. Put it in the fridge, and as it chills, sugar would precipitate out. So you'd have tea with extra sugar at the bottom, kind of like pickles in the brine, right? Extra brine to keep it pickling. You got extra sugar in there. So at any given temperature, you have the maximum sweetness possible because you've got the maximum solubility because you had a super sweetened tea when it was warm. Sometimes you'll go to a coffee shop and they will have what they call a simple syrup. A simple syrup is usually a liquid water that has sugar dissolved into it. And they've maximized the amount of sugar that can be in that water, and when you put sugar in water, you create a syrup. Take that sweet syrup, and it's on the counter. So you've got cream, sugar, and simple syrup. You take that sweet liquid, and you pour that into your drink, hot or cold, and guess what? It's going to dissolve pretty quickly. It's already a liquid. That sugar is already in a solution. So the simple syrup will help you sweeten a cold drink, whereas pouring solid sugar into it will just probably go to the bottom of the glass, and you've got to keep stirring and stirring and stirring and stirring and trying to get those to dissolve. When you're stirring it, what are you doing? You're adding motion. You're adding energy. You're trying to get the water molecules to be able to get in there and separate the sugar molecules so they will dissolve, so that when you drink it, you're getting sugar molecules and tea at the same time because the sugar has dissolved throughout the solution. And you're trying to make it homogeneous so it's sweet everywhere the same. That part of it isn't sweeter than another part of it. It doesn't stratify out. Okay? So that's why there's simple syrups, because you recognize that a lukewarm or even a cold drink, it's very, very difficult to dissolve sugar into that. I was wondering if you were feverishly taking notes or whether you were working ahead.
I'm taking notes. Just so
You're okay. I never quite know. Are you sure they're going to be right? I know. So I was asking your ability to read everybody's handwriting. see if solute is if a gaseous solute is not dissolving well in water, what can you do to increase its solubility? Okay, we just talked about a solid solute in a liquid. What about a gaseous solute? Increase the pressure or decrease the temperature. Right. Make it colder or put it in a pressurized container. It will take the gaseous solute. It's more soluble, so more of it will go into and more of it will stay into solution under cold temperatures and high pressures. Practice problem number 1. It says that hot tubs generally contain water at a temperature of 38 degrees Celsius. To keep the water clean, several solid solutes, say that 7 times fast. Several solid solutes are dissolved in the water. Many hot tub manufacturers warn that if the temperature gets too cold, it will get cloudy and fill with a fine solid. Why? Let's try to get a response from this half of the room. Over here, these 3 rows. Right here. No, it's fine, right? Why would a manufacturer say, like in this case, if the water gets too cold, it will get cloudy and fill with a fine solid? What are they saying? It's going to feel like there's sand on the bottom of the hot tub. It's going to be gritty. Okay? That's what happens. Your hot tub is going to get gritty and the water is going to look cloudy. And the average amateur is going to go, what just got put into my hot tub? Somebody's playing a practical joke on me and they came over and they put sand in my hot tub. But not you. You are savvy Apologia chemistry students, and you understand that something else has happened. What is that something else? What could it be?
It's hot, it dissolves, but when it's colder, it doesn't.
Okay, think through it. Say it again.
When it's hot, it dissolves. When it's cold or colder, it doesn't dissolve it as good.
It doesn't dissolve it as good. As a matter of fact, if it had all of that in it when it was warm and it gets colder, since it can hold less, what happens?
Falls to the bottom.
It precipitates out, right? Okay, so when it precipitates out, it falls to the bottom. And as you get closer and closer to that saturation point, the water appears to get cloudier and cloudier. So like the salt water that we made, it was cloudy. Why? It was saturated. It couldn't hold any more. If we had made the salt water at a maybe 50 or 60 degrees, and we'd heated it up, the water would have actually cleared up. You know, if we made it at one temperature and we increase the temperature, solubility increases, suddenly the water would appear to clear. And as we cool it down, it gets foggier and foggier. What's happening here? As the hot tub water cools, it's reaching saturation. And then when it reaches a point where it's about to become supersaturated, it starts to drop and precipitate out. So it looks cloudy, and then it starts to rain chemical on the bottom of the hot tub. The chemicals that are feeling like that fine sand at the bottom of the hot tub were in there the whole time. But before, because the temperature was warmer, they were able to be in solution. So they didn't feel gritty. Why? Because they were in the water floating all around you. But when the temperature of the water drops, the water can't hold the solids anymore, and they precipitate out, and then they feel like sand at the bottom of the hot tub. So don't go start lobbing paint balloons at your neighbor because they sabotaged your hot tub. That grit had been there the whole time, it just was in solution before. Now it's precipitated out. Number 2. An open glass of soda pop. See? Some people it's soda, some people it's pop, some people it's Coke. right? So here would be a cola Coke. I mean, you don't qualify Coke, right? You qualify an orange Coke, but you don't qualify a Coke. So anyway, an open glass of soda pop sitting on the corner on the counter gets flat. It's less fizzy than the same open glass of soda pop in the refrigerator. Why? Pretty straightforward. Why is it fizzier if you have an open glass on the counter at room temperature and an open glass in the refrigerator, and you take a drink from both of them? The one from the refrigerator is going to be fizzier. Why?
The liquid don't change temperature.
Okay. So there's two different temperatures, right? There's the warm one and the cold one. We're saying the cold one is fizzier. Why? Come on, you can do it. Why is the cold one fizzier? What kind of a solute are we talking about? In soda, the solute is the carbon dioxide, right? The bubbles. So it's a gas. What's the nature of a gaseous solute based on temperature? The colder it is,
Pressure.
no, don't think about pressure. Think about how many bubbles. What does it do with the bubbles? The colder it is, the more or less bubbles it keeps. The colder it is, the more soluble the carbon dioxide is, right? So the colder it is, the more it holds on to the bubbles. The more it holds on to the bubbles means the more when you drink it, you get that fizz in the back of your throat because the bubbles were actually in. And when you think about it, when you drink it, it's cold, you drink about it, suddenly you're 98.6 degrees. You're warm. What's happening in your mouth? The solution is warming and it's releasing the bubbles. That's why you get the fizz as it goes down your throat. Because you are changing the temperature of the solution. You are decreasing the solubility of the gas. It is being released by the solvent out of solution, and you're feeling the bubbles from that. So the soda glass that's open, assuming the pressures are basically the same then, they're both open, the refrigerator glass is going to be fizzier because the colder temperature allowed the sugar water, caramelized sugar water, to hold the bubbles better than the one that was on the counter that was warmer. Okay? From the book it says, soda pop gets flat because the CO2 that is dissolved in it escapes. Since the solubility of gases increases with decreasing temperature, a colder soda pop will hold onto more CO2 than a warm soda pop. And let me go through this. When you no longer have your own in your hand, I can start. You like to compare. You are the compare man. Yeah.
I don't change it. Just compare it.
I think it is.
All right, the substance being dissolved is the group answer. The solute. The substance being dissolved is the solute. The substance into which another substance is dissolved is the solvent, and the combination of those two is called a solution. True or false? Solutes can be solids, liquids, and gases.
True.
That is true. Ionic compounds dissolve into ions, whereas covalent compounds dissolve into molecules. True or false? Purely covalent, nonpolar, covalent molecules dissolve easily in water.
False.
Why? False. It's false because likes dissolve likes. Water is a polar covalent. It dissolves polar covalents. Nonpolar covalents don't dissolve easily because they're opposites. They're not likes. So number 8, solubility is measured in grams of solute per 100 grams of solvent. Grams per 100. It's grams of solvent per 100 grams of solute per 100 grams of solvent. So known as grams per 100. Number 9, a solution in which the maximum amount of solute has been dissolved is known as a saturated solution. And true false, gaseous solutes are less soluble as the solvent warms. That is true. Thank you for your participation.